In this video, we're going to be discussing electrochemistry, and we're going to be looking into how to balance redox reactions and under different type of conditions. So before we get into that, we're going to be just basically doing an introduction here to what electrochemistry is. And electrochemistry is really pertaining to electrochemical reactions that take place. And in those electrochemical reactions, electrons are transferred from one species to another. Now, in your prior chemistry courses, you probably learned about oxidation and reduction. And in this particular case, redox is a very important player in understanding of how first to balance a redox reaction, and ultimately looking at how the electrons are transferred from one species to another. You see the picture here that's on this slide, and you can see that it's a picture of a battery. So basically, we're going to be talking about how batteries function throughout the next set of videos. And so, well, the first thing we want to do is just kind of review what redox means. And in order to do that, we need to first understand what an oxidation number is. So oxidation numbers basically are coming from the elements themselves and how many electrons that they're either have gained or lost during the reaction. So if we look at the reaction that's here with the zinc reacting with the hydrogen ion, the zinc is going to have a 0 oxidation state in the reactants, but if you notice in the products, zinc has a +2 oxidation state, and that's because it's lost 2 electrons to the hydrogen. Now the hydrogen ion goes from +1 to 0 in the products. Now why is it that zinc and hydrogen are both 0 in the reactant and product? Well, because they're in their natural state. So anything that's in its natural state, the oxidation state will be 0. However, when the ions are in solution or they're a part of a compound, the oxidation state typically is not going to be 0. And so that we're going to have to know how to determine that. So that's what we're going to talk about now, is how to assign the oxidation state. All right, assigning oxidation states, we're just going to look at a very simple compound. Let's look at CuCl2, and let's figure out the oxidation state for the copper here. So in order for us to figure this out, we can't just look at the periodic table and say, okay, copper is a certain charge, and we can't do that. So what we have to do is we have to look at the chlorine. Now the chlorine has a -1 charge on the periodic table if you were to look. So just a reminder here. So 1, 2, 0, 1, 2, 3, 4, 3, 2, 1, 0. As you go back down, these are negative, and chlorine is found in this group here. So that's why we know that chlorine is -1. Now there are 2 chlorines, so that means that so if we multiply up, that gives us a -2 charge. Now the overall compound has a 0 charge. It's neutral. So the question is, what does x got to be in order for that to be equal to 0? Well, x is going to be +2, because 2 minus 2 equals 0. Now, if you look at the coppers, there's only one copper in this compound. So for that copper atom, it's going to have an oxidation state of +2 because of what we've seen above. Now, it's not always going to be like that. So if we look at this example here, where we have PbO2, all right, we do the same thing. We set this equal to 0 because the compound is neutral. The charge on the oxygen is -2 because oxygen's found in group 6A, so oxygen's here. And so the charge on the oxygens are going to be equal out to a -4. So x minus 4 equals 0. So the charge on the lead is going to be +4. All right. If we look at a different one, so let's say we have SO4 2-. Well, in this example here, we're going to be looking at the oxidation state for the sulfur. Well, you say, well, it's -2 because if you look at the periodic table, it's -2. It's in group 6A. But you can't do that in this because it's not a metal. So these are two nonmetals bonded together covalently. So sulfur is going to have a different oxidation state than what you normally would find it as if it were an ionic compound. So now this time this is equal to -2 because the charge is -2. The oxygen has a charge of -2. That's always going to stay the same. The only time it's different is if you have O2 as oxygen gas. So since there's 4 oxygens, the overall negative charge is -8. Well, x minus 8 equals -2, so that means x is 6. There's only one sulfur, that means that one sulfur is +6. So the oxidation state of that sulfur is +6. So let's look at another one. Let's say we have NO2 minus 1. So this is nitrate. The charge is -1 because of the -1 charge here. The oxygen's charge is -2. That's -4. X minus 4 equals -1, so X is going to be +3. If we look at the number of nitrogen, there's only one nitrogen, so that's got a +3 oxidation state. So as far as assigning oxidation numbers, we have to look at the compound. We have to first determine if it's metal or non-metal, and then we pay attention to the fact if it's a polyatomic ion. So the first thing we want to do is make sure that we are understanding how to assign oxidation numbers. Now remember that reduction is a gain of electrons, and oxidation is a loss of electrons. So there's a couple ways you can remember this. Oil rig, oxidation is lose, reduction is gain, or you can do LEO, Leo Gur. Leo is the constellation, and it's a lion, so it's going to growl, so Leo Gurs. I know it's kind of weird and silly, but either way, it works. So lose electrons, oxidation, gain electrons, reduction. So these are just a couple different mnemonics you can remember to determine the oxidation state and also determine if it's reduced or oxidized. So as we talk about species that are being oxidized, it's oxidized when it loses electrons. So as we look at the reaction here, we see the zinc going from 0 to +2. So anytime you see a plus charge, you know that you're going to be dealing most likely with oxidation. So in this case, it goes from 0 to +2. So it's losing. So it loses 2 electrons. So therefore, zinc is oxidized. So where zinc is oxidized, the hydrogen atom is going to be reduced because it gains an electron. So if you pay attention to it goes from +1 to 0. Now what we're going to get into is talking about how we balance a redox reaction and using the half reaction method. That's our goal here in the very near future. So if we look at the balanced equation, we can see that there's 2 hydrogen atoms on the left and 2 hydrogen atoms on the right, but each hydrogen atom only loses an electron. So that means that the balancing part where we have 2 hydrogens, that yields 2 electrons. So that way the electrons cancel out. So the one thing that we're going to have to do is we're going to have to understand that when we do balance in these redox reactions, we have to make sure that we balance the electrons. And the electrons are an important thing because we want the electrons to be even and equal on both sides of the reaction when we're done. So a couple last details here are oxidizing agents and reducing agents. So once you figured out a substance reduced, that is called the oxidizing agent. When you find out the substance is oxidized, that is called the reducing agent. So these are kind of opposites, flip-flops from each other. If it's oxidized, it's the reducing agent. If it's reduced, it's the oxidizing agent. So in this case here, the substance that was reduced was hydrogen. So that makes hydrogen the oxidizing agent. Zinc is the reducing agent because itself was being oxidized. Okay, so how do we go about balancing a redox reaction? We are going to be using the half-reaction method. This is the easiest way where we split the reactions in half. I'll explain that here in just a short bit. So before we do that, we've got to get some rules jotted down. So I'm going to go through the next few points, and I want you to jot these down as I skim through them. Remember, you can pause your video as I skim through them. So to do this. All right. Now, in order for us to balance in half reactions, we have to do this on paper, of course, and we're going to be separating the processes out. So getting to the rules here, I'm not going to read these rules to you, but I'm going to pull them up on each slide as I go through. All right, so we are going to be working with a few different reactions. This is one of the reactions that we're going to be working with. So I'm going to do a very simple one here and on this slide before we get to the. In this section, we're going to be talking about how to balance redox reactions using the half reaction method. So in this example, we have aluminum solid reacting with copper plus 2. And during this reaction, it produces aluminum plus 3 ions and copper solid. Now, first thing we need to do is figure out which is reduced and which is oxidized. So looking at the aluminum goes from 0 to plus 3, and the copper goes from plus 2 to 0. So based off of our redox reactions, we can, using the Euler rig or Leerger, we can figure out that copper is being reduced and aluminum is being oxidized because it's becoming more positive. Remember that if you lose an electron, you're losing a negative charge, so that means you become positive, and vice versa. So now what that does, it sets up where we can know which side of the equation to put the electron in, because when we know something's oxidized, it's losing, therefore the electron is going to be a product for aluminum, and in copper it's going to be a reactant. So now we are going to write out the half reaction. So all we're focusing on are aluminum and aluminum plus 3 ion in this first half reaction. Now it was oxidized, it goes from 0 to plus 3, that means it loses 3 electrons. Now for copper goes from plus 2 to 0, and so that gains 2 electrons. One of the rules states is that we need to balance the equation while making sure that the charge of the electrons stay the same. Now you can see that in the first half there's 3 electrons, in the second half there's 2 electrons. So we want to use a multiplier, and a common number is going to be 6 here. So we're going to multiply the first one by 2 and the second one by 3. We're going to carry everything down and cancel out any terms that are the same. So this is going to be a 2 aluminum plus 6 electrons plus 3 copper plus 2 yields 2 aluminum plus 3 plus 6 electrons plus 3 Cu. So we can see that the electrons are balanced. They're going to cross out. Nothing else is going to cross out because they're all solid aqueous, so they're different. So we end up with our half reaction giving us the balanced equation. And so that's how we work with balancing the half reaction method. And so this is just one example that we're going to look at. So this is a very simple reaction. And so once we get into bigger compounds, when I say bigger, I'm talking about a reaction like this where we take permanganate reacting with oxalate to form manganese ions plus CO2. Now, one of the rules here that we looked at in the previous slide was what happens when we have oxygen. So before we get to that, let's look at the oxidation states for manganese and carbon. Notice that the oxygen does not change form. It doesn't go to O2. So we don't have to worry about oxygen, but we use oxygen to figure out the charges of the manganese and carbon. So if we look at the first one here, MnO4 minus 1, I'm just going to show you how to do this real fast. This is -2, that's -8. X minus 8 equals -1. That means manganese is +7. So manganese is +7 on the left, and it's +2 on the right. So it goes from 7 to 2. That means manganese is going to be reduced. Carbon is +3 on the left and +4 on the right. So it's lost an electron. That means carbon is oxidized. And you can see that below there. So we need that information to start our half reactions. So the first half reactions, we look at the carbons, and we have C2O4 yielding CO2. You can see that the oxygens are not balanced in this equation, and in order to balance them, we're just going to put a 2 in front of the CO2. Now, the next thing we want to do is we want to make sure that we balance the electrons. And so one of the things we saw in that first slide is that it goes from +3 to +4. That's an electron. But if you notice that we have 2 carbons on each side, each carbon loses an electron. So therefore, we are going to lose 2 electrons, not 1 electron. It's because of the number of carbons. And that's a little trick, it's a little detail that you have to pay attention to when you're balancing these equations. So now we're going to look at the manganese. So if you look on the left side, you see that there are 4 oxygens. On the right side, there are no oxygens. So what we must do is we must add 4 waters. The reason for adding 4 waters is because there has to be 4 oxygens. So in doing so, what else do we see that we add in that we don't have on the left side now? The hydrogens. There are 8 hydrogens on the right, so we need to have 8 hydrogens on the left. You got to keep it balanced on both sides, depending on what you add here and add over the other side. So here we are, we have the 8 hydrogens. So all of our elements are balanced now, but what we need to do is focus on the electrons. So in order to do that, we have to go back and remember that we are gaining 5 electrons. So we're going to put 5 electrons on the left side. So we have our half reactions written out. We see that we have 5 electrons in this half reaction. On the carbon's half reaction, there are 2 electrons. A common number between those two are 10. So what we're going to do is we are going to distribute throughout the half reactions. So that way we have 10 electrons. And here's what we've done. So the distribution has been done. So we're going to bring down everything on the left, and we're going to bring down everything that's on the right. And what we ought to see are the electrons should be the same. And if we were to go through and check each of the elements, so if we look at the hydrogens on each side, there are 16 hydrogens on the left. If you look on the right hand side, if you look right here, there are 16 hydrogens there. So you can just check yourself to make sure you have the right number. So the electrons are going to, of course, naturally cancel out because they're even on both sides. That's going to come really important when we get into galvanic cells in the next video. So subtracting them out, we are left with this final result here, where we have the reactants and the products, and this is a balanced redox reaction. Now, one other detail that I want you to make sure you understand here is that we didn't specify it, but this is under an acidic solution. So when you're dealing with solutions that are acidic, you want to have hydrogen ions left over. So what happens if you're dealing with a basic solution? You do everything the way you do it in the past few slides. That doesn't change. But what does change is in the very end where you have your hydrogen ions. You have to neutralize the hydrogen ions with a hydroxide ion. And so in doing so, we're going to produce water on both sides so we can subtract out that water. So we're going to look at another example that involves balancing redox reactions and dealing with a basic solution. So I'm going to flip to a new slide here in just a second. In this problem, we're going to work out a solution that's basic, and we're going to balance it using the half-reaction method. So in order to do this, what we have to do is we have to first figure out which is reduced and which is oxidized. So let's do that. So first of all, we look at I minus, and so the iodine is -1 on the left side. It's 0 on the right-hand side. So I goes from -1 to 0. So what's that tell us? That tells us that this substance is oxidized because it's becoming more positive. Now we look at the manganese. The manganese goes from +7 to +4. So the manganese goes from 7 to 4. So that's going down. That means manganese is reduced. And of course it's reduced because iodine is oxidized. So if we pay attention, we're just going to work out the iodine since we don't have to deal with water here. So the iodine, there are 2 on the right hand side. But if you notice on the left hand side, there's only 1. So we need a 2 in front of that. Now since it's being oxidized, it loses an electron. But since we have 2 iodines, we need to make sure we balance out that electron with a 2. So that takes care of the iodine's half reaction. Now we're going to look at the manganese. So you have MnO4 yields MnO2. So notice that there are 4 oxygens on the left and there's 2 oxygens on the right. So we need to add 2 waters. Now we have 2 waters, that gives me 4 hydrogens, so we need to add 4 hydrogens on the left. If we were dealing with an acidic solution, we would be done with this reaction right now, but it's not an acidic solution, so what we have to do is we have to balance out the hydrogens with hydroxide. So we're going to add 4 hydroxides on the left hand side. I'm going to underline that because that's what we're adding in because it's a basic solution. Whatever we add on the left, we need to add it on the right as well. So we have 4 hydroxides on the left. Now this is going to produce 4 waters. And so what we're going to have happen here is the 4 waters is going to subtract out with the 2 waters on the right hand side. And that leaves you with 2 waters. So I'm just going to write this down here, make it a little bit neater here. So we have 2 waters plus the permanganate yields MnO2 plus 4 hydroxides. And the last thing we want to do here is we want to put our electrons in. So it goes from 7 to 4. That means it's going to gain 3 electrons. And so now we want to balance the electrons out. There are 2 electrons in the iodine reaction, and there's 3 electrons here, so a common number is 6. So we're going to multiply this by 2, and we're going to multiply this one by 3. We're going to carry everything down. So we have 6I minus plus 6 electrons plus 4 H2O plus 2 MnO4. All I'm doing is the reactants first. Now I'm going to do the products for both half reactions, putting them together. That leaves me with 3I2 plus 6 electrons plus 2 MnO2 plus 8 OH minus. Now if we look, we have 6 electrons on both sides. They cancel out, and everything else is left over. So we have 6I minus plus 4 H2O plus 2 MnO4 minus yields 3I2 plus 2 MnO2 plus 8 OH minus. So this is the balanced equation. And the other information we get from this is that it transferred 6 electrons. Remember, that's something that we'll be using in a future video. So it's important that we understand first how to balance the half reaction using the half reaction method, and then knowing how many electrons are transferred, so that way we can utilize that information in the future topic. Do as many of these problems as you can find online. The more you do, the better you're going to get at it. Thanks.